Okay, here we are. This is actually a request from a student from the calc class. So this is going to be jumping way ahead. I plan to do more videos with a previous instruction, but this is from chapter 6 in the Finney and Thomas calc book. This is actually chapter 6 point. Here, let me see. It's a it's chapter 6.4 or 6.4, number 7, right? And we're essentially integrating functions or exponential functions and etc. So this again was a specific number requested by a student. So let me just go ahead and explain a little bit. Majority of the time, or I want to say predominantly, you're going to be using U substitution. You always think U substitution. So essentially, the way we can start this or take start off with this is let's set U equal to something. And it's always going to be kind of this guy right here, the exponential, right? So we have U equals to 1/2 x. Again, x over 2 is 1/2 x, right? And if we differentiate U, right, because again, U substitution, we write everything in terms of U, and that means that dx has to be replaced with du, and anything with x is U, right? And including the limits of integration, these guys right here, right? They have to be modified to reconcile reconcile the difference between x and the change from x to u. So let's finish this off. So du equals to, what is it, 1/2 dx, right? And then we can just solve for dx. So just carry the 2 over to the other side. So 2 du equals to dx, right? So now let's replace everything or substitute. Oh no, one more thing. Let's take the limits of integration, right? Okay, let me write this. So, okay, if I have, so hard to write a straight line. All right, score. All right, in the original function, 1/2 x, ln of 4. We have our limits of integration are ln of 4 and ln of 9 as specified, right? Now, when x is ln of 4, the initial or the new what's the limit, right, of integration for u will be ln of what, 2, right? If you guys don't see where I got that from, let me do it on the side. 1/2, and we're gonna evaluate this for ln of 4, right? And we know by law of exponents and logs, right, that the exponent, the coefficient in front now becomes an exponent, so you have ln of 4 to the 1/2, right? Or simply ln of 2, right? And the same goes for ln of 9. So we have ln of 9, so that'll be ln of 3. Cool? So now we have essentially our new elements. Everything changed and replaced new, and then we just have to substitute everything now. So our new integral, including the limits of integration, the new limits of integration, don't ever forget those. That's where people go wrong usually. They forget the limits of integration. And then we have e of u, right? And we also have the constant. We have dx equals to 2 du. We can set du here, right? Because we're just replacing dx. And then we could go ahead and set 2 outside of the integral, right? So this is essentially a new function or a new integral. Now let's go ahead and solve for that. So we know that the integral of e to the x is simply what? E to the x plus c, right? But because we have a definite evaluation of integration, then we're going to use, we don't have that plus c, we actually have this interval that we're going to be working with. So we have 2, let me rewrite that, 2, and then, right, e to the u from ln of 2 to ln of 3, right? That's essentially what I'm saying, is 2 times all this guy right here, right? Now, 2 e to the ln of 3, right? Minus e to the ln of 2 equals to what? 2. And then we're going to know by logarithmic properties that we have a base right here of what's really log of e. We can just drop it, simply just 3 minus 2, right? Or 2 times 1 equals to 2. And that's your answer. That's your answer, right? Okay, let's maybe try one more, and I'll cut this video short and work on some other methods. Let me see. 6 minutes. Okay, yeah, I think we could do one more, right? I'm gonna go take this one. It's actually number 9. Number 9 is a really good one. This extends to so many different areas. Well, number 9 does. Once you kind of get number 9, you're going to see this a lot, especially in Calc 2. This type of this ideal. Okay, so number 9. Again, 6.4, section 6.4, or chapter and section 6.4. So we have e the root 2. Oh, not root 2. Sorry. Over root r, and then dr. Right? Okay. One fundamental thing to notice is that, or take observation of, is that whether the integral is definite or indefinite, and right now we have an indefinite integral, so you always remember to put plus c. Just that's a key feature of these guys, right? Okay. U. We can set u. I mean, it's kind of obvious. U would be root r, right? Now, the beauty of that is that when we differentiate u, right, that's 1/2 r to the negative 1/2, right? So we're essentially, anytime you, dr, sorry. Anytime you differentiate a root, right, or a square root, you're always going to end up with 1 over that square root in the expression after you differentiate it, as we have here. So we have now 1/2, right, or 1 over 2 root r, right? 1 over 2 root r, right? And that's the beauty to differentiating these square roots. So always keep that in mind, is that you're always going to have that 1/2 minus 1 equals to 1/2, right? And you're always negative 1/2. So you're going to always have this component on the bottom, which then thus allows us, according to u substitution, the rule of u substitution, the key feature is that you have to have whenever you differentiate u, you're going to have its derivative, right, present inside the equation in order to substitute. And we do that. We have that, right? And then because we have 1/2 right here, that's essentially a constant that just can be pulled out. Now we can substitute everything in terms of u, and we are assured that this can be replaced after differentiating u. So let's replace that, right? And we have no limits of integration, so don't worry about that. Let's see. Oh, it's e to the u, right? Because we have u equals to root r, right? And then we have, I'm just going to simply put, dr. What am I doing? Oh, we can take this like this, watch. So we're going to simply move the 2 over, right? And just have 1 over root r dr, right? So this entire component, or this bunch of stuff right here, is actually present in the original integral, right? So we have du, right, equals to 2 right here. So we don't even have to, there's nothing going under here, because we've replaced dr, sorry, I'm not lost, but a loss of words, there you go. This has been replaced with du, right? So now that we have that all in place and everything settled, then we could just simply just integrate e, right? E to the u plus c. And then what's u? Replace u. We said it was root r. 2e to root r plus c. Let me check, make sure I'm right. Okay, I'm back, sorry. Yeah, that was the right answer. I checked in the back of the book. So, yeah, so that's it. I'm going to stop right there. I'll do some more, but I don't want to run these videos too long. I don't want to overuse my time. So, 11 minutes is fair. Okay, so keep that in mind. I'll see if I can look through, rummage through these problems, find something a little bit more significant. Again, the student asked me in particular to review the entire chapter, so I'm going to try to go over various concepts if I can throughout the chapter, and maybe settle some things that and elucidate some misconceptions, usually where students find difficulty, and hopefully resolve those issues into something that they can handle a little bit more and understand better. These concepts are very difficult at this stage, especially when you've worked with so much of this within 10 to 16 weeks. Anyways, so take care. I'll be back.